In this video, we're going to talk about suggested homework problems from 8.8, improper integrals. Let's go ahead and get started here. Talk about what an improper integral is first. Question 1, describe 2 ways for an integral to be improper. So we could have option 1, 1 or both of the limits of integration are infinite. That's the most common type. Second type is there are a finite number of infinite discontinuities then the bounds of integration, limits of integration. Interval. It's probably the best word here, interval of integration. Okay, so let's look at number 3. Explain how to deal with a improper integral that has an infinite limit of integration. So we've got 3 cases. We've got if it's in the form of a to infinity, f of x dx, and is continuous on a to infinity, then we replace the upper limit with a dummy variable b and let b go to infinity. If we have integral negative infinity to b, f of x, and f of x is continuous on the interval negative infinity to b, we can take the limit as a goes to negative infinity of a to b f of x dx. So we'll deal with how to handle the situation where both limits are infinite later in the assignment, but that's just what they wanted you to do. Either if you have a negative infinity, replace it with an a and take the limit as a goes to negative infinity. If you have an upper limit of infinity, replace it with b and let b go to infinity. Let's look at number 5. Number 5 asks if the integral is improper, and if so, why? So let's look at the domain of the integrand. So there's my domain, but 3/5 is within the bounds of integration there, the interval of integration. So improper because there is an infinite discontinuity at x equals 3/5, and 3/5 is between 0 and 1. So number 7. Integral 0 to 1, 2x minus 5 over x squared minus 5x plus 6 dx. X squared minus 5x plus 6 equals 0, minus 2 and minus 3. So x equals 2 or x equals 3. 2 and 3 are not in the interval there, so 2x minus 5 over x squared minus 5x plus 6 is continuous on 0 to 1, so the interval is proper. I will say is not improper. Since we haven't really defined proper, we've only defined improper. Nine, 0 to 2, e to the negative x dx is not improper because e to the negative x is continuous on 0 to 2. 11, integral negative infinity to infinity, sine x over 4 plus x squared dx, improper because both limits are infinite. Thirteen, 0 to 4, 1 over root x dx. And they give us a picture here. You can see that it's approaching a vertical asymptote from the right. So I can only come at 0 from the right. So this is going to be limit as a approaches 0 from the right of a to 4, x to the negative 1/2 dx. Limit as a approaches 0 from the right, x to the 1/2 times 2, a to 4 is 2 square root of 4 minus limit as a approaches 0 from the right, 2 square root of a is going to be 2 times 2 minus 0 is 4. So this converges. Let's look at 15. Zero to 2, 1 over x minus 1 squared dx. And we're going to have to break this up. 0 to 1 from the left, 1 over x minus 1 squared dx plus 1 from the right, to 2, 1 over x minus 1 squared dx. This is limit as b approaches 1 from the left of integral 0 to b, x minus 1 to the negative second, plus limit as a approaches 1 from the right, integral a to 2, x minus 1 to the negative second, dx on both of these, limit as b approaches 1 from the left, of a negative x minus 1 from 0 to b, plus limit as a approaches 1 from the right, negative x minus 1, this is to the negative 1, a to 2, limit as b approaches 1 from the left of negative b minus 1 to the negative 1, plus negative 1 to the negative 1, plus limit as a goes to 1 from the right of a negative 1 to the negative 1, plus a negative 1. Nope, this is an a. Plus a minus 1 to the negative 1. So this is limit as b goes to 1 from the left of negative 1 over b minus 1. The reciprocal of negative 1 is negative 1, plus limit as a goes to 1 from the right of reciprocal of 1 is 1 times negative 1 is negative 1, plus 1 over a minus 1. So looking at the graph of y equals 1 over x minus 1, which looks like this. I'm looking at the graph of y equals negative 1 over x minus 1, which looks like this. Then the limit of this function as I approach 1 from the left is going to be positive infinity minus 1 plus a negative 1. And then looking at this one as I approach 1 from the right is also positive infinity. So this is approaching positive infinity, and this diverges. Let's look now at number 17. 17 says 2 to infinity, 1 over x cubed dx. So I'll need limit as b goes to infinity, 2 to b of x to the negative third dx. And that will be x to the negative second over negative 2. 2 to b, limit as b goes to infinity. So limit as b goes to infinity of a negative 1/2, and then b to the negative second brings it down, plus, and then 2 times 2 squared, that's 2 cubed. So that's going to be 0 plus 1/8 is 1/8, and that converges. I didn't say so on the last problem that went to infinity. That one diverges. Let's look at number 21. Integral 0 to infinity, e to the x over 3 dx. Need a 1/3, and I need a 3. let's go ahead and look at 3 integral e to the u du, where u is equal to x over 3, du is equal to 1/3 dx. Let's look at this indefinite integral first, see what happens, and then we'll make it definite. This is 3e to the u plus c, which would be 3e to the x over 3 plus c would be my capital F of x for my antiderivative. I need the limit as b goes to infinity. Of 3e to the x over 3 from 0 to b is 3e limit as b goes to infinity of 3e to the b over 3 minus 3e to the 0 is infinity minus 3 is still infinity, and this diverges. Look at 23. 23 is the integral from 0 to infinity of x squared e to the negative x dx. So just looking at this part here, and I'll worry about the limits of integration later. So b goes to infinity, 0 to b, x squared e to the negative x dx. U is equal to x squared, dv is e to the negative x dx, du is 2x dx, v is a negative e to the negative x. So u times v is 2x, sorry, it's x squared e to the negative x minus the integral of v du, which is a 2x e to the negative x dx. So that's equal to x squared e to the negative x plus 2 integral x e to the negative x dx, and we'll integrate by parts again. U is equal to x, dv is e to the negative x dx, du is dx, v is negative e to the negative x. This is x squared e to the negative x plus 2 times, and then uv, negative x e to the negative x minus the integral v du, so that'll be plus integral e to the negative x dx. Distribute that 2, x squared e to the negative x minus 2x e to the negative x plus 2 integral e to the negative x dx. So this is equal to x squared e to the negative x minus 2x e to the negative x plus 2, I'm sorry, minus 2e to the negative x. And then I would say plus c. Let me rewrite this though as x squared minus 2x minus 2 over e to the x plus c. I want to see if I got all my signs right there. So uv should be negative. uv minus the integral v du. So that should be positive. Pull the 2 out. Then this should be 2 times uv, which should be negative here. And then minus the integral v du, and those will make a positive. So that's a -2 and a +2, and then that becomes negative. So let's see here, I have a f of x that equals this. I want to find the definite integral now of this. So definite integral from 0 to b, limit as b goes to infinity of x squared e to the negative x dx should be equal to negative x squared minus 2x minus 2 over e to the x, limit as b goes to infinity of 0 to b. That should be equal to a negative b squared minus 2b minus 2 over e to the b, limit as b goes to infinity. And then this should be minus, and then this would be 0, 0, -2 over 1. So this is going to be, by L'Hopital's rule, limit as b goes to infinity, negative b squared minus 2b minus 2 over e to the b equals 0, because the quadratic in the top grows slower than the exponential in the bottom. Right now, exponentials are the fastest growing functions that we know about. They're in the denominator. The numerator is essentially like a constant to it, and we could just use L'Hopital's rule a couple of times here to get the top to go to a constant. The exponential would keep coming back and it would go to 0. So this is a negative, -2, which is 2 for my limit, and so it converges. Let's look at number 27. Here's the first time that we have infinite limits at both the lower and upper limit. So I'm going to need to pick a number in the middle of the interval that I'll call C, that's between A and B. Pick C such that C is between A and B, and F is continuous at C. Okay, so I'm just going to pick negative infinity to 0. And you may remember this property of intervals here, that we can split intervals up like so. And then I want limit as a goes to negative infinity of a to 0, 4 over 16 plus x squared dx, plus limit as b goes to infinity, 0 to b, 4 over 16 plus x squared dx. And This is going to be 4 arctangent of x over 4. And this is over 4. And this is going to be when as a goes to negative infinity. This is evaluated from a to 0 plus limit as b goes to infinity of 4 over 4 arctangent of x over 4, 0 to b. The limit as a goes to infinity of arctangent of 0 minus arctangent of a over 4 plus limit as b goes to infinity of arctangent of b over 4 minus arctangent of 0. Arctangent of 0 is 0. So this is limit as a goes to negative infinity. This is a negative infinity. Times the negative arctangent of a over 4 plus limit as b goes to infinity of arctangent of b over 4 is going to be negative limit of arctangent of x as x goes to negative infinity plus limit as of arctangent of x as x goes to positive infinity. So arctangent, if you don't remember what it looks like, has horizontal asymptotes at pi over 2 and negative pi over 2. Horizontal asymptote to the left here is a negative pi over 2, so this is negative pi over 2 plus pi over 2 is pi over 2 plus pi over 2 is pi. Let's look now at 29. Nine is 0 to infinity, 1 over e to the x plus e to the negative x dx. Going to rewrite that as 0 to infinity, e to the x dx over e to the x squared plus 1. That'll be 1 squared. So I have a u of e to the x, a du of e to the x dx, an a squared of 1, an a of 1, and a u squared of e to the 2x or e to the x squared. So this is the same as the integral of du over u squared plus a squared, which we know is 1 over a arctangent of u over a plus c. So this would be equal to 1 over 1 is 1 arctangent of u over 1 is u. So this is equal to tangent of e to the x. So this will be limit as e goes to infinity of arc tangent of e to the x from 0 to b. It's going to be limit b goes to infinity, arc tangent of e to the b minus arc tangent of e to the 0. So this is the same thing as limit as x goes to infinity of arc tangent of x, since e to the b going to infinity is going to infinity. The exponential graph goes to infinity to the right, minus arc tangent of 1. So this is going to be pi over 2. As we looked at the graph of arc tangent before, it has a horizontal asymptote of pi over 2. And minus pi over 4 is 2 pi over 4 minus pi over 4 is equal to pi over 4. So now at 63, y equals negative 7 over x minus 1 cubed. X is between negative infinity and negative 1 is included, where we have a asymptote over here at positive 1, but we're not getting there, so we're fine. We're continuous on this entire interval. So the area of interest is going to be negative infinity to negative 1 of negative 7 over x minus 1 to the third. I can rewrite as negative 7. Limit as a goes to negative infinity of a to the negative 1, x minus 1 to the negative third dx. So I'll make this negative 7, x minus 1, limit as a goes to negative infinity, x minus 1 to the negative second over negative 2. This is evaluated from a to negative 1. This is 7 halves, limit as a goes to negative infinity of negative 1 minus 1 is negative 2 to the negative second, minus a minus 1 to the negative second is going to be 7 halves. Limit a goes to negative infinity of 1/4 minus 1 over a minus 1 squared is going to be 7 halves of 1/4 minus 0. And that's going to be 7/8. And this will be units squared. Let's go ahead and look at 69. 69 says, find the arc length of the graph y equals square root of 16 minus x squared. Y prime will be 2 over root 16 minus x squared times the derivative of the inside is a negative 2x. 2's will cancel, give me negative x over root 16 minus x squared. Y prime squared is x squared over 16 minus x squared. My arc length formula is 0 to 4 square root of 1 plus y prime squared. Now the problem here is going to be that x cannot be equal to negative 4 or 4 right here because of the 16 minus x squared that's in the denominator. So I need s to be equal to limit as b goes to 4 from the left of 0 to b of, and now I'll make 16 minus x squared plus x squared over 16 minus x squared dx. This be s is equal to limit as b goes to 4 from the left, 0 to b of square root of 16 is 4, root 16 minus x squared dx. I'll pull the 4 out front. S is equal to 4, limit b goes to 4 from the left of 0 to b, 1 dx over root 16 minus x squared. A squared is equal to 16, a is equal to 4, u squared is equal to x squared, u is equal to x, du is equal to dx. So this is an arc sine situation. S is equal to 4 times limit as b goes to 4 from the left of arc sine of x over 4 evaluated from 0 to b. S is equal to 4, limit as b goes to 4 from the left, arc sine of b over 4 minus 4 arc sine of 0. Arc sine of 0 is 0. So S is equal to 4 arc sine of 1 is 4 times pi over 2. 2 goes into 4 2 times, and this is 2 pi, and we're done. So we'll come back next time and talk about suggested homework problems from 9.1, which are sequences. And sequences are functions whose domain is the natural numbers, the counting numbers. They're well ordered because we plug in 1, 2, 3, 4, so on. They have a first element, a second element, a third element, and can be ordered like that. Every once in a while, we'll have a sequence that we will index starting at 0 because it's more convenient, but really the natural numbers and the whole numbers have the same size, and it's also a well-ordered set, and it's basically the same thing, but the definition is going to say that the domain needs to be the natural numbers. So we'll come back and we'll talk about that. The whole point of talking about the sequences is so that we can get to a limit definition for something called a series. And that will be our next big topic in chapter 9 is sequences and series, but mostly series and convergence and divergence of series. So you saw the word converge and diverge in this section here in 8.8, as we talked about whether an integral converges and goes to a number, or whether an integral diverges and goes to plus or minus infinity. Same idea with a series there later. So that's our next big topic. So see you for the next video.